After some discussion, I start this talk. Okay, the situation is very, very, very interesting. Now, the you and the Hungarians are at different level, and I mean not level. So you learn different things right now a little bit. With the Hungarians, I will discuss this. I will discuss this with you later. This is actually the very end. Gábor Lente is the director of your institute, and I sent him an email and asked what to teach you. And there were two things that he suggested. One thing is something about reaction, kinetics, equation of reactions and everything. I don't understand exactly. It's something 30 pages. Last night I started. That's sociometric reaction equations. I cannot even pronounce. Do you know what is it?
Yes.
You learned it from him?
Not from him, no.
At the end, we will learn it. We have still 4 classes together. I mean 4 weeks, more classes. I have now a long slides, 22 pages, and today and tomorrow we will discuss what is on these slides, and we will see. Okay, so now I skip this. I started to discuss something that's eigenvalues, eigenvectors, the organization of linear transformations. So that was when I talked about mirroring for plane, mirroring something for a line, mirroring something projecting something to a line, rotations, projection of space vectors, and also mirroring of space vectors. So all of these transformators were and are linear. I explained you what is this, so what happened when you do the transformations. That's okay. When you have a 0, when you have 1, when you have a -1 eigenvalue. Which is new is the reorganization of this linear transformation. So what's this? The first was yeah, I again forget to change T to M. Okay. So this is and you just mirroring everything to this line. Here, that's vector A, and I have another vector. This vector A is parallel with this A line, B perpendicular to this E line. And then, if you make the basis, I mean that's a coordinate system actually, then you can do the refraction of any vector. No, it's with this transformation. So if you just do this transformation, or with R, not A, it's disturbing. Okay, so this is the diagonal form of the transformation matrix. Okay, that was mirroring for what is it? For a line. Okay, next one is projection for a line in 2D. We also have this A that's parallel. A. We have B that's non-zero and also what is it? Also perpendicular. Okay. From the definition of projection, projection means you have a P operator, you apply vice, and for any vector, then after if you apply at least vice for a vector, you got the same vector. And for A, it's PA is equal A. For B, because it's perpendicular, it's 0. So from this, we can construct the matrix. That's if you check. Okay, if you check this, then this is a this is R10. So if this is in the system of or the values of A and B. So all vectors are in this system. So in this system, the matrix is this one.
This is the projection, right?
This is the projection for a line in a plane.
Projection.
Projection.
Projection isn't, I mean, what I feel of a projection is dot product. When you dot product something, like as we do F dot D, that means how much work is being done into the direction of the force.
This is okay. We brought the projection in scalar form,
yeah,
but you can write it in matrix form.
Vector form.
Also, something you missed, the vectorial product could be write as a matrix.
Mm-hmm.
And because of this, it is a linear transformation.
Okay, got it.
We had something similar once when I wrote the different projection and I wrote them down as a dyadic product. That was before. Well, this is not exactly for you, but the Hungarian class is frightened because of the eigenvalue problem and the diagonalization, and I just want to show you something that is not understandable without calculation. They're really frightened. They also frightened because of the test. I mean the exam, because they never had deduction before, but actually they did in the secondary school. So I demonstrated them they can do it, but I don't know. I know your country. I don't know your country, but most of the chemistry students are female, and they are not really self-convicted, so they need some encouragement to believe they can pass the exams and do everything. It's not necessarily in Scandinavia or Belgium or in the Netherlands that women are strong. So it's and they do whatever they want. Okay, this is interesting because when a long time ago in September I started the linear algebra, then for the operators there was an example, the rotation. It is not written, but this is a rotation transformation, and this is quite special actually. If you not consider special angles, which is the multiplication of 19 degree or 180 degree or something like this, then you will not have invariant, you will not have eigenvectors. But except if the vectors are on the axis, for example, for here on axis x. You can write something similar, but it's not really a nice form. And I think I made a mistake. I talked about spin once, and so I told you that the spin 2, 3, 4 means you have to turn around a body to get more than one to get the same orientation. It exists, but it's not for 2, 3, but for one of the 1/3 half spin. So not for the bosons, it's for the fermions and the quarks. And also there was something I talked about, the macroscopic object that is a spin. Its spin is a half. Actually, it's a macroscopic object, but it has one unstable and one stable point. It was something different. So I misunderstood something, but it's not important here in this class. Yeah, so this is not a diagonal form. However, and actually we had done something similar in the test, midterm test. This is the mirroring of mirroring of a vectoring of 3D vector for a plane, and this. Okay, it's more difficult. To me, I mean to draw. That's S. That's a plane. At least it's supposed to be. And this plane has one vector, a perpendicular vector, and also there is something that's perpendicular, that's C. So you have this A, B, C basis where and then if you are in this plane, you can do the sorry. This is not the mirror. This is the projection. The coordinate system is the same. So if you have an R vector and you want to project it, then the perpendicular part, which is parallel to C, that is eliminated, and only the parallel part with the A and B will remain. Therefore, the projection matrix will be this. And if you check this, then you will have And this is exactly what I wrote down there, which is not nice. No, doesn't matter. Okay, so. And now mirror for this plan. So it's the same. You have something that is here, something perpendicular, and the third perpendicular, and you can write the same Okay, so we are looking for something that needs this mirror stuff. If you have an R vector, then if you are in this system and you need the mirror, then in this system the C coordinate will change. So the mirror operation will be, it's the same, it's the opposite. So if you do the calculation, you got this that we expected. So I don't know, not last time, but 1 week ago, I just wrote down the linear transformations, projection for line, mirroring for line, rotation, projecting for planes, and everything. I hope you remember it. In the slides, you will find it in appropriate order, and it is written. But okay, then this is the diagonalization, because you can do it. You also can write quadratic form and everything, but I don't feel it has sense. There will be this geometric stuff. Also, there is something that SVB and Gabo Lente brought me to talk about it. And there will be two other topics, but if we want pass, it doesn't matter. Okay. Last Thursday I started this, but I didn't finish. And some of you was not here, so I can repeat. It is very useful if you can do this LLU decomposition. What does it mean? It means that you have a matrix and you made two matrices, lower triangular and upper triangular matrices. Actually, it has some name like low echelon triangular form or something like this. What does it mean? It means that the upper triangular means there is no non-zero element below the main diagonal. The lower diagonal means there is no non-zero element above the main diagonal. The triangular matrices are very comfortable. It's easy to invert them, it's easy to multiply them, it's easy to calculate the determinant, so it's a nice thing. The problem is the following: so the problem is that not always possible to do this decomposition. If you do this decomposition, it's not unique, but for certain conditions, when the matrix could be inverted, then it's possible to prove that the decomposition is unique and exists. Doesn't matter, still it's a useful thing. What I wrote here is interesting. Actually, I had done this example last time. You have a matrix and you can transform a matrix to upper triangular form. It's called Gauss expansion. It's a way to fix system of linear equations. Now it has its own life. It's moved from the source, and this method could be used independently, and because of this, it has consequences. Very interesting stuff, actually. What you can do, the method is the following. You transform the A matrix to an upper triangular matrix. That's okay. You wrote down all transformation, and then you multiply all transformation, and from that transformation you can get the lower triangular matrix, and you can do this decomposition. It is written here, blah blah blah. Okay, but which is important is the example. Okay, I told you what is it. Great. Okay. It has a definition, array decomposition. You have an n times n matrix, and you can write into the form of product of lower triangular and upper triangular decomposition. Okay, I told you not all matrix has array decomposition. It is not unique, and you can show if A invertible and has an array decomposition, then it's unique. Okay, so here an example. I had started this and fixed this actually last time. So this will be just a repeat, but the end. So I didn't finish this actually. Oh, and I also destroyed the room. So tomorrow perhaps we will we will have a practice, a seminar in ruins or something like this. I will check this when I go back whether we have a sheet or not, but we don't have sheet here, so we can leave it out. So last time I tried to adjust the sheet and then it failed, almost hit me, but finally I survived and everyone else in the room survived, so that was a dangerous first day.
So we're going to try it again.
Sorry?
Are we going to try it again? Tomorrow?
Tomorrow?
Yeah.
No, I will not destroy the room again, so I don't want. At least try, but you know, sometimes it's difficult. Okay. So let's start. We have an A matrix. And I do the Gauss extension. What is the first? The first is subtract, no. Sorry?
1 minus 1 half.
Yes, thank you. And the matrix was something, was it this one? I guess it was. This is, ow. So I will have the following. That's the same. That's the same. Then that's 0. Then this is 2. This is 2. And this is 0. And this is the same. Okay, then that's you. Thank you. And this matrix is I think we should do something the curtain where I can switch on the light. It's okay. Okay, so when I do this, it's the same. This is also the same. But here it's 0, and then 1, and then sorry, 1, and then 2. Okay, now I want to eliminate this one. So I do this, and the transformation, it means Oops. Is this okay? Okay. Good.
Yeah, it's okay.
Okay. So, okay. Now it is understandable what I'm doing. It's okay. So I can do the math. If you do the calculation, that's interesting actually. There is no proof or anything deduction, but if you just copy the numbers from the matrix, this is A1, A2, A3 to there, then, oh, I forgot something. You have to do the inversion, of course, and then from these, you got that one. So this is not A1, it's inverse A1, inverse A2, inverse A3, and you got that one. And that is L, so this is the decomposition of our matrix. We have done this, we are happy, and we should be happy. Why? This method didn't use anything on the right side. I mean, if you have equation, then you can use it multiple times. Additionally, if you go back, then the difference between A and B is just deleting one column. And we didn't do anything, didn't change anything between columns. So one solution is good for the other solution. Therefore, the method for the other is just deleting that column. So it's 2 in 1 or infinity number of solution we have right now. There are more about this LU decomposition, but because you don't know, because you wasn't here, I checked the physical chemistry and the other stuff on the page of Chemical Institute. All the slides are there, and I find only a few applications of this this course.
In chemistry.
In chemistry. For you, that's okay, but you are the only physicist, but also we have I have the same with the Hungarians. There is one physics student and 9 chemistry students. So I don't feel that I should give you more deduction and more detailed explanation of this. because you will not use it. Sometimes you will use because what Gabor Enke sent me, there is linear independency, and also there is some matrix inversion in this metric method, whatever it is. I have to learn the pronunciation. Okay, there is something, it's algorithm for L decomposition. It is written, but that is what I had done. That is you must have to do. I will find and give you practice, and we will practice this L decomposition with more matrices. We will do it. Also, you can prove the existence and uniqueness of this L decomposition. You can check in the literature. Actually, this vector, the Hungarian note. This guy is very, very important, and I didn't recognize him. There is a book about LaTeX. LaTeX is a typesetting system, and I learned it first from there. Now I use internet, and this vector is one of the author of that book. By the way, you told me you can't, you don't develop softwares, and you can't program it. You cannot develop a code or something like this. But did you learn R?
No, but we've heard about it, but no, we didn't.
Because the Hungarians did this something with R codes, R methods, but with double length. So I asked what development environment they use, but they didn't know. So this afternoon I will do this. So I don't know what, but I will do something different with them.
By the way, Professor, what is the application? Is there any kind of application of?
You can write reaction equations like 2 hydrogen plus 1 oxygen, and then you got 2 water. And you can write this somehow down. You can develop a matrix, and then you can do something with it. But I didn't get what you can do it. But I will. Don't worry.
What we do in the physics is that, like in mathematics, let's say, we have set of equations, and we make an augmented matrix.
Yes.
And then we do the row echelon form or echelon form. What is it called?
That's.
Is it echelon or what? No.
It's echelon form, but I wrote something different, like upper triangular and lower triangular, but it's echelon form.
Exactly. Yeah. So it helps us to determine the value of the unknown variables, right? But in this scenario, like we inverted the E matrices and multiplied by U, what will we get? I mean, there is no use to do
there is. Now I start to do it, and this is what I had no time to finish last time. You can easily fix a system of linear equations with this, easier than normal way, and also you can do matrix inversion with it, easier, because of the row echelon form. That's an easy form to handle a matrix. That's why you had snakes and triangular and diagonal form of matrix and everything a few weeks ago. Okay, what we will do here? Now we fixed this, and we have an LU decomposition. Great. You have an equation, this A times X equal B, it's a system of linear equations. You can write it down like this Ux is Y, and for the Y you have another equation. Well, it looks a bit difficult, but if you in the A matrix, you have a lot of numbers. But in L and U, you have less numbers and more simplified to do any operation with them. So, the method is the following. You have an equation, and this equation is divided into two equations, and if these two equations, you can fix these equations, then you can fix the original equations. You right now know one value decomposition, and you can use it. Okay? Let's continue with this. This okay. We have this example. Okay, I don't need to write anything. So if you check this example, then this is the matrix B. And first you want to, just a moment. Yeah. You have this equation, and you first fix another equation. This is the lower triangular or lower echelon form. Oh, this is not equal, it's just a mistake. Okay, let's fix this. Actually, if you do this, then great. Then you have great. Then the last one, I do the multiplication. Okay, so I fixed this equation. It was quite easy because I didn't use any Gauss method or matrix inversion or anything advanced techniques that or method that I taught you in the last semester and the previous weeks. Okay, now we fix the first equation, and now we can fix the second. That's out. What is it? It's and here it's also not equal, it's a dot, just and this is the y that we fixed there. Okay, so this is not a quantum theory. Yes, so this is so with linear efforts, we fix this linear equation, system of linear equations. And if you change the numbers, the vector b, you can do it in the same way. It's easy. So this is the meaning of this. I always told you in linear algebra, the coding and the numerical analysis is very close to this. So somehow this should be pitched together. But if you use this paper to do the laboratory notes and reports and everything, you really use this millimeter. Is it really serious? Do you understand? Do you know what they are doing? So if they are fit a function or measurements or something like this, they use this paper with
Graphs.
graph.
Graphical paper, I know. There are boxes.
But did you use it at the university? They use it. Do you also use the Stonex or something like this, or
I use Origin or some programming to plot some data. Right?
of course.
We asked if we could use Excel to plot, but they said no.
The Excel is also good. This is better than nothing. You can do a lot of things with Excel. Actually, when I went to the European Space Agency, I learned how to use this data query and fitting, and there are a lot of things, but people don't know it. Actually, when I, for example, correct your tests, then I do the grades with some function that is programmed. I also do some operations. I do not calculate everything by hand. Okay, so now we are at the LU decomposition. I don't know how much time we have. 7 minutes. Sorry for being late. Okay. Now we continue this with matrix inversion, because the matrix inversion is also easier with LU decomposition. What you will do, we will do, not do, we, but use the correct English form. Okay. We also do the same in 2 steps. We divide the inversion in 2 steps. First, we do the inversion for an intermediate matrix, this Y, with the U, with the L, what is it? The L matrix, and then with the solution we do the same with the U matrix. And I was wrong. We do not do any inversion. We just fixing linear system of linear regulations. This is the LU decomposition. That's fine. Do you remember? It's okay. Then you start with this. What is this? This is the Rohr form Luber triangular matrix, and I multiply it with the general matrix, and I want to do the eigen matrix, identical matrix. Okay, I will do it. It's too difficult. This is so weird. This board. It's like fatty or shiny, or so even writing with the chalk is not a good feeling. That is good, but this is also bad. Okay, but it's not your problem. Okay, we have this. So first we can do the multiplication, and we have a result. Okay, then just a moment. I have You can do in this way. I don't like it. I do in other way. Oh, no. I'm wrong. I am wrong. I did the wrong stuff. Great. You can do this. That's okay. This is okay. This is fine. Then
you're finding the eigenvalue, right?
yes, I'm finding the eigenvalue, but the
You have to multiply.
no.
Just not it.
Wait. Okay, there are many things. So then there is this.
One row and one row.
I don't like this. Just a moment. If you do the calculation, the row and column, you will get this. Okay, then next row. Then here. Oh, no. No, no. No, no. Okay. Time is up. And I will continue this tomorrow from here. You wrote it down?
Yes.
Okay, I also recorded it. So I will continue from here. Thank you very much.